Question 4. A hollow toy boat is floating in a bath. If you take a teaspoonful of water out of the bath and put it in the boat, what happens to the water level in the bath? The level goes down, the level goes up, the level stays the same, or there isn't enough information to say. So basically, in order to solve this question, what we want is some kind of expression that relates the volume increase or decrease of the bath versus the volume increase or decrease of the displaced volume, and then comparing those two things should allow us to determine whether or not the water level rises or falls. So hopefully that makes sense. So let's draw a diagram. So here's the bath. Here's the boat. Consider the mass of the boat is m, therefore the weight is mg. And by Archimedes' principle, we know that mg equals the volume displaced currently times by rho subscript w, the density of the water, times g. And that tells us that the displaced volume currently, before we do anything, is just m divided by rho subscript w. Okay, so that's our initial volume displaced before we do anything. And now what we need is a new displaced volume once we put the teaspoonful of water from the bath into the boat. Now, just to make this a bit more general, let's consider an arbitrary volume of an arbitrary object from the bath. So it doesn't have to be water. It could be something like a rock. So let's just say the mass of this rock, which could be any arbitrary object, is its density times its volume. And now we want a new expression for the displaced volume. So V goes to basically m plus m rock, because we've taken, say, a rock or something from the bath, any object. This could be a droplet of water as well, so we'll get to that a bit later on. I'm putting that in the bath. So now I've got m plus m rock. Okay, so that's m over rho w plus rho subscript r v subscript r over rho subscript w. And that equals v, which is the original displaced volume, plus rho r over rho w vr, where this term here represents effectively the additional volume displaced once you put the object in the bath from the water. Now in the question, we're taking a teaspoonful of water. So actually, in our case here, rho r equals rho w. Our arbitrary object density, which we call the rock, but we can call it whatever we want, is actually just a teaspoonful of water. So actually, the density is just rho w. And that means this additional term, in our case, is just VR, or the volume of the rock, or the volume of the arbitrary object we removed from the bath. Now what does that mean? It means precisely the volume that we removed from this bath, and therefore the level will have decreased. Once we put that volume back in, the displaced volume brings it right back up to where it was before. So actually, the answer is C, the level stays the same. Now, what's a more interesting question is, and we can intuitively check our answers here, what if instead of a teaspoonful of water, we had simply some kind of incredibly dense rock, but it was really, really tiny. Now, what that would mean is that we have this special case, which I'll put down at the bottom, which would be rho rock is much, much greater than rho W. And that would mean our extra term on the end would be much greater than our original volume. And in this case, what does that mean? Well, we get a whole extra bit of displacement of water here, and therefore the water level would rise. So that's in the case where we've got a really heavy rock. And intuitively that makes sense, right? You take a tiny little rock out of the water, but it's incredibly heavy, it will push the water level up. So hopefully all that makes sense. But in this case, of course, we are just taking a teaspoon of water. Oops, I've highlighted the wrong one there. We're just taking a teaspoon of water. So actually, rho R just equals rho W, and therefore the additional displacement is equal to the amount of the volume that we remove from the system. So the amount we remove equals the volume we then add, so the water level stays the same.